About a month ago, I blew out the original board on my new Ender 3. And through experimentation, I found out that 3 of the stepper drivers had been damaged. The X-axis, the Z-axis, and the extruder motor stepper drivers no longer worked. So I purchased another Melzi2 board, Banggood, I think, and replaced it. And so I had this, and I thought I'd take a stab at fixing it. So I also obtained a separate display, and so with this, configured up a little jumper cable, bought a NEMA 17 stepper, and then a 24-volt power supply. So basically, I have the guts of the printer without the printer chassis. It has Tim Hoogland's quite excellent unified framework on it. And so I thought, well, I don't have anything to lose. If this board is dead, then it's dead. And okay, fine, it was a learning experience. But since my background is in digital electronics and I've fabricated many boards, I thought I'd go ahead and try a manual repair. Now, the replacement chips, I purchased 5 off DigiKey, and so here are the replacement stepper motor drivers. I've already used one. And to make sure that this worked, I've already replaced the X motor driver. That's why it doesn't have the heatsink. But let me show you kind of the methodology and some of the highlights of exactly how you do this. We're going to be somewhat limited in how close in I can zoom on these little QFN packages. And in general, I try to avoid QFN packages because there's so much trouble to work with. The trouble to work with, that is, if you're trying to do this manually. QFP packages are fine, and you can manually accomplish surface mount soldering. I do it with 0805s all the time. I have done it with 402s. I've never successfully soldered a QFN package with this type of pitch until today. So let me show you the methodology to demonstrate this. So I have my simple little test bench here. And what I'll do is come over here. I just powered up the system. We'll go to prepare, and then we'll do an auto home. Now, the stepper motor is connected to the Y axis driver, and so at some point in time, we're going, and keep in mind, there are no limit switches on this, and so the amount of motion that you can get is limited, but it will tell us as whether or not we're talking through that channel. So I'm going to go ahead and say, prepare, auto home, and there we zeroed the Y-axis. Now, because the stepper, the Y limit switch defaults to being closed, it just moves a tiny bit. All right, so what I'm going to do here is I'm going to go ahead and power off. I've got my power supply plugged into a power strip. It's probably unnecessary, but I just waited for it to power down. I'm going to unplug the Y-axis, plug it into X. Keep in mind, this is the chip that I've replaced about 30 minutes ago. Power up my system again. Prepare, auto home. And so the repair of that, the replacement and resoldering of that chip worked as it moved to what it thought was the X home position. So now, what you do, the basic steps that I'll work through, I'll show you, and I'll zoom in when I can, just as much as I can. The tools that you'll need for this, of course, you'll need ideally a hot air rework station. Now the reason for that is because the the little stepper motor drivers have a solder pad on the bottom side. So basically, the whole board, the whole chip has to be heated up hot enough to reflow the solder on the pad. So obviously you need some replacement stepper motor chips. You'll need it helps if you have a test bench set up something like this, because then you can know whether or not you've successfully completed it. But it is pretty much required that you're going to need a hot air rework station. This is mine right here. And it has both the hot air wand as well as a very fine tip soldering iron, which I'll show you later. The toothbrush is for cleaning off the surface with acetone once it gets cleaned up. You'll need some appropriate solder paste. This happens to be a bismuth-based solder paste, so I don't need to apply quite as much heat when I begin my reflow operation. You'll need some sort of fine point. Here is just a fine tip needle, and you'll need that for moving solder paste around, because obviously you can't screen this when it's got all of this stuff around it. Just the likelihood of doing that is very small. You will at least need a magnifying glass. This is sort of the smallest one that I have. It's a little bit unwieldy for this. And then a lot of the work I do underneath my binocular microscope. This is something I assembled a few years ago, and then I added to it a light ring. And so I mounted it underneath a shelf with a pull-out strip of hot rolled steel. And this allows me to position the microscope beyond the table, so that if I need to position something manually, I can do so. And then when I'm working on the bench, I simply slide it back. And it's worked quite well. You'll also need some solder paste. Some flux. I've had this around for many years now. The handy part about it is that it contains a brush. And so we'll use that a little bit later as I clean up. Just some simple solder, it doesn't really matter what, but we'll use that when tinning the end of the iron, because we're going to, after the chip is in place and we think that it's soldered in, then I'm going to go through with the tip of the soldering iron and do a reflow. And unless the tip of the iron is recently tinned, it's not going to reflow very well. All right, so the basic operation, and I've already done it with two, since I was able to successfully repair the x-axis as kind of a test, I re-verified with my little test bench here that the z-axis and the extruder stepper are also damaged. And so basically all I did was take a pair of long nose pliers, and you just grab the heatsink like thus and twist. And obviously you don't want to pull so hard straight up that you pull the chip off the board, and because if you do that, it's likely you've ruined the traces on the board, and so the board is dead. So if you apply a little twisting motion, just kind of rotate it around, it'll start loosening up, and then pretty soon it'll pop off. The adhesive that they use is not that much. It doesn't stick very well. It's enough to hold the heatsink in while it's not, there's no mechanical forces to eliminate it, to move it. Okay, so basically then I took my tweezers and started scraping away the adhesive and then cleaning that up with acetone. So I'll get back to you when I've completed that operation. So here's what the Z-axis driver looks like when it's just been cleaned off carefully. You have to be patient with this. You don't want to scrape so hard that you damage the traces. Here I used a combination of the needle and X-Acto knife, and you can see that most of it comes off pretty well. I'm going to do the same with the with the Y-axis driver, or sorry, the Z-axis driver, and then clean them up with acetone. All right, so here we have the Z-axis and the extruder stepper motor drivers pretty much cleaned off. It's important that you get as much of that white glue out from between the pins as you can, so I would suggest picking away at it carefully and patiently with something very small. The reason is we're going to be melting this off with hot air. The glue is going to deteriorate and burn, and it would be, I think, better if we kept that as much away from these joints as possible. There'd be less cleanup, less probability of that kind of getting in the way when we go to reflow our board. So the next step will be to set up the hot air reflow and try to lift one of these chips off the board. Okay, I've preheated the hot air rework station, and so it's now cycling. It's stable at close to 300 degrees C. So now it's going to be a little bit clumsy holding the camera phone and then also reflowing, but here we go. So what we're going to look for is the solder is going to start to when the solder melts, it gets kind of shiny. And then I'll set the hot air rework down and see if the chip is okay. So the second chip came off nice and clean. So now what you want to do is you want to take your toothbrush and acetone and clean off the remaining used flux. You don't want to use solder wick and remove the remaining solder. We want to leave as much solder in place as possible. That's going to be important when we reflow. So I'm going to clean this up and then I'll get to the next step. I dunked the toothbrush in some acetone, and so now we're just kind of cleaning up here. That'll get rid of any of the remaining residue. Now, the strategy that we have at this point is we don't care for the next reflow operation if we reflow the outside pins. We're very concerned to get the pad. So I'm going to take a little bit of solder paste from the syringe. This is my tin bismuth, and just put down a tiny bit in the center, and literally that's about enough. And you want to try to keep it away from the edges. There, that's enough. It might be too much. So now what you do is you use your magnifying glass or your microscope. Try to spread the solder paste out in the center of the pad, because once it gets hot enough to reflow, it's going to reflow to the edges of the pad. If you have too much in one place, like I do on the right-hand side, I'm going to be wiping some of that off with a needle. It will tend to join to the outside pins, and then you're just dead in the water. There's really no way to fix that except for starting over. And you can only heat up this PCB and cool it down so many times before the copper starts lifting off the substrate. So I'm going to clean this up and get it ready and then come back. Okay, here are my new chips. Now it's important to orient the chips so that probably couldn't do that if I had to, so that they're in line, they're oriented toward how they're going to fit onto the board. So the alignment dot is in the upper left-hand corner, and here is our alignment dot on the PCB. I'm going to grab the other one and just get it close. Now, this really needs to be done under a good magnifying glass or the microscope. I'm going to be positioning this under the microscope. By the way, one of the reasons for using flux is that it's sticky. It's going to help the chip stay in place because as it begins to evaporate, it acts a little bit as an adhesive, and so it helps hold solder mask surface mount chips in place. So anyways, I'm going to go ahead and position these and then take another picture. All right, under my binocular microscope, I've positioned the two QFN packages so that they're aligned on all four sides with the pin. You have to be very patient and a very steady hand at this point because you want the pins to be perfectly aligned. To be off even a few thousandths of an inch, you risk causing the pads to breach. So now I'm going to turn the air down on my hot air reflow to about there. I have a small nozzle, and now what we're looking for, let me zoom in just a touch. I'm going to take the hot air. We have to come straight down onto the chip because otherwise the chip is small enough that it will begin blowing away. I had to do this just like that. So I have to reposition the chip. Before I do that, I'm just going to go ahead and go over to this one. And what we're looking for is for the solder to start getting glossy and hopefully for the chip to sort of sink down onto the previous solder and the extra solder paste that I put on. There, you see the solder glistening. I had to rework the Y stepper motor driver. I either didn't have it quite positioned correctly or it moved during the initial reflow. But I now have both the Y and the Z chip there, and then the extruder chip. So these are now soldered from the air reflow. The ground pad on the bottom of the chip is attached, and there was enough solder left on the PCB pads to reflow to many of the pads. Now, the trick that we're going to use is we're going to use the tip of the soldering iron. This is a very fine tip iron. And I'm just going to kind of show you the technique. Well, first of all, let me go ahead and tin this. Hang on. All right. I have the tip of the soldering iron recently tinned. So what I'm going to do is simply position the tip of the iron and just drag it slowly along the side of the chip. Now, if I've done that correctly and there's an adequate amount of solder, that looks pretty good. I'm going to be checking it from a side angle. We're not able to see quite enough of the chip, but that looks pretty good. So I'm going to complete that. You see over on this other side, we've got some pins that bridged from the reflow to get it connected to the ground pad. Once I drag along there at a correct pace, it's very likely that that solder bridge will be removed. If not, then you'll have to use just a touch of solder braid. But I'm going to do that for all of these and then get back with you. All right, at long last, I have the pins reflowed. Took a little while to clear a bridge on the Z driver. I used some fine solder braid, but I actually had to cut it down to make it narrower and then turn up the heat on the iron because I wasn't getting enough heat to actually wick solder out from between the pins. So it's pretty much ready to test, and we'll see if the Z driver and the extruder driver are ready to go. All right, so we're ready for our power on test. I've got the Z-axis connected to our test stepper, and I've got the monitor here, so we're going to do an auto home. Good. And so even though the limit switches are not in place, it did try to move the stepper motors. It wouldn't do that if the chip wasn't hooked up correctly. So anyways, you have to have a good reason for switching out the chips like this. A QFN package is a lot of trouble to change. It's easy enough to take it off. You just heat it up with the hot air reflow and lift it off. Getting it realigned and resoldered back in place, making sure that there are no shorts between the pins, that takes some work, takes some patience. You need some optical enhancement, either a microscope or a good magnifying glass. I've seen some of the electronic microscopes now, the digital microscopes. Those are pretty cool. But you have to have something in order to inspect it once you're finished, to make sure that you don't wipe out the rest of the board with a short or something like that. That would not be good. So anyways, it looks like now I have a backup board. If I remember correctly, the firmware doesn't allow me to exercise the extruder stepper unless it sees that the extruder is hot. There is an override, but I'm not connected right now to send that override to the controller. So I think that I've got 3 good chips replaced out of 3, and I'm ready to use this as a backup when needed. As I mentioned, the firmware normally, without the override, will not allow the extruder motor to run unless the thermistor sees that the head has temperature. So I wired up a small test lead. The extruder temperature on the Melzi board is input through this connector right here. And so it's just a simple mating connector with a 100K trimmer. So I'm going to mount this, and then we're going to do a test. For convenience, I squeeze the trimmer inside of the vise with the stepper motor. And so now we're able to see it. I have it adjusted here so it shows that it has a fake temperature. So as I trim this, if I turn it counterclockwise, it acts like the temperature is going up in this particular case. If I turn it clockwise, it brings the temperature down. But let's just put it around, high 190s. So this is fine. It just shows that the head is hot. So now let us do a test to test our extruder channel. We're going to do move axis, extruder. We'll go ahead and move 10 millimeter units. And so our E channel is working. So now that that's established, that's working. I had now a known good backup board, and I'll go ahead and glue the heatsink in place. So thanks very much.